Dr. Andrew Orry, senior scientist from Molsoft LLC, who joins us on his first ever visit to India and will be presenting on Inside Molsoft ICM, combining artificial intelligence and physics for next generation molecular discovery. Dr. Andrew Orry earned his PhD in biophysics from the University of London, UK, and has valuable industry experience with leading pharmaceutical companies including GSK and Merck. We will welcome Dr. Andrew Orry with a round of applause.
Yeah, the title of my talk is Using ICM to Combine Artificial Intelligence and Physics for Drug Design, Drug Development. The focus of my talk really is going to be on the very new features that are coming into ICM. I think some of you may have already been using what we call the beta version 3.94a. If you're not, please contact Surjit and he can send you a download link and you can use it. Some of these new tools we haven't shown anybody else before, so we saved it for the Indian audience, and we'll try to encourage our USA people to come here next time. You never know, we'll see. So I want to start really, it's my first time in India and I've had an absolutely amazing time. Beautiful people, beautiful country, and wonderful food. A little bit noisy with all the honking and stuff, but I got used to that part, but that's fine. And honestly, I want to thank Surjit and Preetha and the whole team at Advent for their hard work in putting this together. It's a really amazing achievement what they've done. Before I met Surjit, I think it was just me and Dr. Chincha, Sinjin, if you're here. Thank you at the back. And the other guy, Dr. Anand, in your team, and Dr. Srinivas. And also that was at Sinjin, and also at Origin, we had Dr. Sunil, who took a risk on ICM. I don't know if he's here as well, but I think he might be. So those are the original ICM users, and we were so grateful to them. There were some other academic ones, but that was basically it. And I spoke to Surjit, and he told me that he was going to get India to use ICM. I didn't quite believe him, but he's doing a good job. So we're very grateful for everybody's support and for coming today, and really appreciate it. So everything I'm going to show today is really the development from Ruben Abagan, who's obviously spoke earlier. That's over 40 years of research from his team into internal coordinate mechanics. And he's had a long-term collaboration, obviously, with Max Totroff, who is our Chief Technology Officer. And combined, they published the early papers on ICM, internal coordinate mechanics, and the bias probability Monte Carlo method as well. Some of you may also be familiar with Eugene Rausch, who's our principal developer. He's an excellent developer, and he generally tries to fix things in 12 hours, usually. It's quite astonishing. The other key members are Arman, who's heavily involved, a developer in ICM, and Polo Lam, who's not in the picture. He's our chemist and also photographer. So he took this photograph. So he's a very talented chemist. So these are the key guys. So the topics I'm going to talk about are starting off with our new neural network generator of site-specific R groups. Some of you, I think, may have found it hidden in the beta version. I'll describe how it works. There's also R group decoration and de novo design as well, which we will discuss. I'm going to talk about Giga Search, which is the fastest substructure and fingerprint search on the market. We originally developed that for Enemy when they had the real database, but now it's super fast search. And then I'm going to talk about new tools for peptide design and modeling. So and with CombiRidge, which is relatively new from a few months ago, and also a new tool which I hope is going to make Surjit's support team very happy. So hold on for that one. Okay, so we're going to start first with this new neural network site-specific R group method we call Group Gen. It's a neural network trained to generate a binding moiety. So the input is like you have a bond vector in a 3D sort of context, so it's shown here. And then the output is a generated R group of 2D structures. So the way the model is built, we have an encoder, a 3D graph convolution neural network, and it inspects the 3D receptor context around a root bond vector and creates a latent pocket embedding. And then we have the decoder, which sprouts the chemical 2D modifications to that input. The decoder is trained on the R groups, and the encoder is trained on the PDB complexes that we have. So the R group decoration tool initially is actually embedded in the ICM 3D ligand editor. If you haven't found it or you haven't used it, it's in the ligand edit tab, and I'll try to show it to you in a minute. So you can just run it. You just have a complex of your ligand and receptor, and then the tool generates a pool of potentially favorable substituents based in a 3D context. So I'm going to try and show you just quickly that in ICM. Just 1 second. We'll see if this works. Okay. Okay, so here we have the ICM 3D ligand editor. I've already jumped a couple of steps. You may be familiar with setting up the ligand here and setting up the receptor. So everything is set up to run. And so basically to use this new AI tool, you just need to go to the Advanced tab and choose the option AI Decoration. And then have a number of AI steps. So obviously the more you choose, the longer it's going to take and the more rigorous it's going to be. And you can also choose how many compounds you want to score. This is a pretty fast approach. You just go OK, and it will run in the ICM workspace. It should be a few seconds. So this is using the encoder and decoder. It's taking the points at each point around the ligand. And we have a table now. It took a few seconds. And it's a completely de novo design of modifications. You can see the table here. It's ranked. You have different scoring. We have the RT-CNN score, which is our neural network score. You have the physics-based score. And we have what we call the score combined, which is a combination of the physics-based and the RT-CNN score, which is the neural network score. And we found through our studies that the combined scoring is sometimes the best approach. So this is fully interactive. You can rank it by score. Just double click and it loads your new design in. And you also get a strain value, which is quite useful sometimes just to double check you haven't designed something that's unrealistic in the pocket environment. And there's also a synthesizability score. So for this AI stuff, it's important to be able to eventually be able to synthesize it in an efficient way. So this score, the closer the score is to 1, the more likely it is to be available to synthesize. So just going to go back to this. Yes. So the same technology is also available in the docking menu, and it's more rigorous, and it's going to give you de novo ligand design. Rather, in the 3D ligand editor, it's just making modifications around the ligand. But in the docking menu with this new method called ligand aid, it's a fully de novo ligand generation directly in the binding pocket. So your starting point for this is a population of docked small fragments. Those are inbuilt into ICM. This generates a cohort of new designs with R groups added or replaced by the group gen network in the previous slide, as well as some atom substitutions from an atom predictor. The generated designs are then redocked, and then there's some kind of Darwinian selection process which involves removing those that have poor score, poor physics-based score, drug-like list properties that are poor, or synthesizability. So that gets rid of a number of different tools. And you'll find this option in the docking menu. I've mentioned RTCNN score, so did Ruben earlier. It outperforms our own physics-based score, but we found, as I mentioned, you can combine the physics-based score and RTCNN score for a very good improved docking score. Using this CASF benchmark, ICM outperforms many other software, including Glide, for the ability to redock accurately, as well as ranking the structures in a virtual screening scenario. Moving on to a different topic. So Giga Search is also now available to anyone who has ICM Pro plus VLS or ICM Chemist. It's embedded there. If you use it in ICM Pro or ICM Chemist, it goes to our website and runs the search. So please don't, although it's fully, we don't see anything, just be careful with any proprietary information. But it's also available as a separate product that you could purchase from Advent and place it on your own servers and run it locally. So it's just as fast. It's the fastest. You should be able to do searching by substructure and fingerprint in like 5 to 8 seconds. And you can also use a full suite of filters and sort of property tools. So you can use smiles and smarts to enhance your search. Like chemical patterns, binding properties, atom types, and connectivity and that kind of thing. So on our Molsoft website, we have ChemSpace. We've worked very closely with the guys at ChemSpace, the Freedom Space. We're very grateful to them for allowing us to host this. And Enamine Real Space is there as well. And we also have MQL and Zinc. I just want to show you where this is in ICM. So if you go to the search tab, you first need to download the latest ICM version, which you can get from Surjit. Click here, and you can then see online databases, and you'll see the list of online databases here that you can use. And then you can sketch your query. Just choose like pyrimidine or something. You just click here. You can say you want an attachment point. If you right click on an atom, say attachment point. You can add other queries. So if you want another ring, find this pyrimidine connected to another ring. You can right click on the atom and choose ring membership 2. So that atom will be in two rings. And then you go search. Now, the internet's a bit slow here, but I'll give it a go. We'll see. It may take a bit of time. You should get like about 500 hits or so, but the connection I think is very very slow, so it's probably not going to be too quick. We'll come back to that. So the next topic I'd like to just cover some very new tools that we developed for one of our biotech customers who specialize in helicons and development of small peptides, is adapting the small molecule ligand editor to make it easier to use for peptide design. So in the past, when you loaded in a peptide, it would be displayed as a chemical, so a very large chemical display. So now we have tools where you can load in the peptide, and the peptide will keep the peptide bonds, and you'll clearly see your modifications. So inside there's residue. You can modify residues. You can delete residues on your peptides. You can do other functions, which I'll show. So one good example is 7-UWI, which is a beta-catenin in complex with a helicon peptide. If you get the latest version, you could try this example. Sometimes when you read in a PDB with a peptide, the peptide is shown as one molecule, and if you have a linker or a staple, sometimes it's shown as a separate molecule. So we have a way now to merge those into one single peptide. And then all you need to do is go to the ligand editor tab, same as what you do for the small molecules, but choose the option peptide mode. And I'll show you that quickly in a second. And then you can modify the peptide. So you get these nice images where you can clearly see the chain and any staples that you have. You can delete residues. You can add terminators like acetyl groups, NH2 caps. You can optimize both the peptide as well as the receptor. And you can insert one or more residues as you choose. You can play around with different modifications. So you can right-click on a residue in your peptide and just choose a natural amino acid, or you can choose an unnatural. We have a whole database of unnatural extended amino acids. And then every modification you make, you can, as with the small molecules, you can just place it in a table, and that table is fully interactive, so you can always go back to it and display your peptide. And as before with the ligand, with the small molecules, full, undo, and redo. So you can just play around with different ideas and explore different peptide chemistry. Once you make your modifications, there's some new minimization tools. You can relax the peptide to fix any covalent geometry issues. So if you're adding a staple or you're adding a group, there's always going to be some things you need to clean up a little bit. So this needs a convenient button there to clean that up and relax the geometry. If you have a helix that you know is part of your peptide, you can sort of reinforce that helix and tighten it to make sure it stays as a helix. You can minimize torsions and side chains, and you can optimize both the side chain of the ligand and the receptor. And while you do this, you can continuously monitor the RTC and N score and any strain. You can also add a staple. So if you want to sort of reinforce the rigidity of your peptide, you can staple it. You can add a staple replaces two residues and creates a covalent link. You just select one residue, and then you get a database of potential staples, depending on, and you can then define how far you want your staple to go, like 4 residues up or 7 residues up, and it'll automatically build it, and then you can minimize it and evaluate the score. We have several predefined staples embedded in ICM and other sort of specialty chemistries there, and custom staples at the moment can be added, and we'd be happy to help. There's a little bit of tweaking needs done, but that's because this is brand new, and we can definitely add them for you. I just want to quickly show you this in ICM, so in case you want to do this later. Okay, so this is again already set up. You use the edit tab. You set up your ligand here, and you choose the peptide mode, okay, and choose the peptide from your PDB, and then it will be set up. And then you'll see that in the lig edit, we have a number of different options. So if, for example, you can see here at the end, we have 2 residues that look a little bit disordered. So you can just right-click on them and choose delete residue, like this. Like this, and then you can evaluate the score. You can do some minimization. You click and hold here. We can relax the geometry a little bit. We can minimize the torsions. And you can see the score here. So the ligand strain you have in small molecules, generally we say between 5 and 10. But peptides, you can be a little bit less restrictive, and maybe up to 15 would be a good value. But obviously, as before in small molecule, the lower the docking, the lower the RT-CNN score, the better the predicted interaction. So if you've made this design and you want to share it with your colleagues, you can just add it to a chemical spreadsheet by clicking here. Well, now it's a peptide spreadsheet. So you can see the peptide here, and you can change it. If we rotate this molecule, we will see that there's a leucine that is making a lot of contact with the receptor. So you may want to play around with different modifications with that. So simply to do that, you right click on the ligand. You choose, we could choose an unnatural residue, amino acid, and maybe we want a lipophilic one or something. So we could just choose uncheck aromatics. There's quite a few, you see. These are entries here. We can say we don't want any charges on our modifications, we want it uncharged. We could say we're not interested in the D form. We could say we want only 11 heavy atoms, or up to 11 heavy atoms. So you can filter here as well. Or you can search directly the code for the residue that you want to try. So we could try CYPG, just click on here and go OK, and it will make that modification in 3D. If we add this to the table, we'll see in our little sketch here that the CYPG has been added at this point. Then you could do some things around that molecule. So you could say, oh, we have this tyrosine here. Maybe we could build a hydrogen bond between the tyrosine and the modification we just added. So maybe an oxygen atom at this point might be a good modification. So we have a number of tools here on the right-hand side. And you can, as before with the small molecules, you can just click on an atom, click on the where you want to modify it. This could be critical because I can't see very well. And yeah, so we made the modification. So if we wanted to, we can just, if we wanted to look for sort of more weaker hydrogen bonds, we can change the values here. But if we want to say maybe optimize this tyrosine and see this hydrogen flip round, ideally, we can right click on the tyrosine on the receptor and optimize that residue. And we can also optimize the modification we just made on the ligand, on the peptide, in the same way. And then we should see a hydrogen bond. We didn't see it. Let me just check. Yeah, it needs a little bit more optimization, but you should eventually see this flip round and make the hydrogen bond. Let me just double check what's going on. Yeah. Okay, I maybe missed an atom, but you should see a hydrogen bond. So basically is the tools. There's a variety of options here that you can install a staple, you can insert residues, you can delete residues as I showed, and you can also add terminal groups as well. So that's a very new thing that we've added to ICM in the last week or so. So CombiRidge has been in use now for, we use it a lot in our contract research projects, and there was also a webinar about it a few months ago. And CombiRidge is I think it's definitely the most powerful tool at the moment for screening in a structure-based way libraries of like giga-sized libraries, so billions and trillions of compounds. It involves three main components: Ridge, which Surjit mentioned, and I think Ruben mentioned as well, which is our new GPU-based docking. It is the fastest docking available, structure-based docking on the market. It's the same as the regular docking you use on a CPU, except that it uses pre-generated conformers and runs on a GPU. So if you have ICM Pro plus VLS, you have the same methodology, except you're using fully flexible ligand. In this process, you generate conformers for your ligands. It also uses Ginger, which is a generative neural network method for producing accurate and diverse conformer ensembles. There was a paper last year describing that, and also the RTCNN method as well. So the CombiRidge workflow is very straightforward. Step one has been done for you for a large number of databases. If you have a new database, we'd be happy to do step one for you if we can share it with other users. So that's step one, is taking the anchors, these small molecules, the fragments basically, and generating the conformers of those fragments. I'll show you the databases we have available in a minute. Step two is how you usually start CombiRidge. It's just one line of code, or you it's one line of ICM commands basically. You just cut and paste and set the job running. The docking anchors are docs using Ridge. And then there is an enumeration step and minimization step in the pocket. And then the physics-based score is there. I just wanted to show you visually in ICM as well. Yeah, so practically speaking, you take your protein structure, your docking projects that you already have developed, that you maybe used for your CPU docking. Everything is exactly the same. You just use that docking project. You then you can then run, if you wanted to, you can run a pocket finder to locate the pocket, and then the a bit carried away with the pockets. So you can dock the fragments that we've developed for you, and then these are ranked and scored. So here's one, and then we have the additional ones. And then after you've ranked and scored the fragments, you start generatively docking. The ICM starts to build the full molecule without enumerating the full library, but just going to the chemical space and generating these new hits, which you can then score and rank and purchase from the vendors. So some of the advantages of CombiRidge is that you go beyond the chemical catalog. You're opening chemical space that is not easily searched using traditional tools. You can screen large databases more efficiently. Chemical synthetic feasibility is built into the process from start to finish, so you shouldn't have to worry too much about the synthesizability of your compounds that you're seeing, of your hits. And then sometimes we find that the initial fragment docking step actually identifies subcavities that you may have missed when docking the full ligand. So the fragment fits into a small cavity, and you may not find that cavity if you're docking the full ligand without the fragment step. And in our contract research projects with Big Pharma, we've actually got a hit in every single screen we've done, and some of them have been significantly high as well, like a substantial hit rate of over 50% in some of the projects. We're hoping that they'll let us publish, but I doubt. We will see if that's possible. But basically, it uses the same process. All you need to do this is at Molsoft, most of us have these gamer desktops for research, not games, but they usually have these good GPUs, 4090s in them. You need like at least 8 cores of CPU, which is kind of standard in modern computers. And you would need an ICM. You need to go to Surjet and ask him for an ICM Pro plus VLS, Ginger and Ridge license. And at the moment, Combi Ridge only runs on Linux. The chemical spaces that you can screen are ChemSpace, 140 billion, enamine, 48, it has 45 million anchors, the enamine real, and 48 billion compounds in total. So the anchors are the fragments that you dock initially. And then there's the Wuxi database as well. And we're working currently with XtalPi, in China, and eMolecules to add their database for you to use as well. So I just want to end on one thing that I hope is going to be quite useful to our especially Shamsher and DTO and Surjet's team. We've developed a new AI assistant for ICM. So it's fully trained on the manuals and fully trained on our knowledge base. So you can use it to write scripts. And so I just want to quickly show that. Oh gosh, it's logged me out. Let's see, no, it's not. Yeah, just 1 second, sorry. And actually, I think if you go to the ICM support site now, you will see it. But don't use it because just everybody using it at one time might not be good. We'll see. But so yeah, you can type things like write me a script to read in PDBs on my local drive, convert to function F1. Yeah, thank you, Sergey. My local drive and convert to an ICM object and calculate pockets or something like that. And it's thinking. It should be quite quick. Yeah, and then it gives you a script. So yeah, it's kind of it's kind of cool. Obviously, as with Ruben's demonstration of AI at the end of his talk, nothing's perfect. There may be some little bits of troubleshooting you may need to do, which is fine. And if you let us know, we have this ability to let it know that it's made some mistakes, and we can fix that as well. And yeah, please feel free to use it. I think if you go to the support site, it should be there, maybe at the bottom of the screen. So just wanted to definitely thank Surjet and for the amazing job you've done, and everybody here, thank you very much.
Thank you, Dr. Andy.